So this lecture series will be about, well, broadly about symmetry in quantum system. So I will begin by discussing the dynamical implications of symmetries in quantum system, like quantum mechanics or simple quantum field theory. And later on, I'm going to explore two new kinds of symmetry, which is called generalized symmetries. Okay. So, well, let me begin by defining what is an anomaly. So, well, first of all, I'm going to focus on, can I actually write it? Okay, that's a bit weird. So, well, just the eraser. So let me begin by the symmetry in quantum mechanics. So in quantum mechanics, we learned that the symmetry, so we are given a Hamiltonian in quantum mechanics. And symmetry is wherever the commute the Hamiltonian. So if you have unitary symmetry, then let's say the generator is U, then UH equal to HU. So that's how we say there's a symmetry. Symmetry in quantum mechanics. Oh, okay. And so the set of symmetries will generate a group. So the set of symmetry will generate a group. Okay. And well, interesting, what's the dynamical consequence of the symmetry? So here I'm going to focus on symmetries that admit an inverse. So today we are going to focus on symmetry with inverse. The inverse. Okay. Now, one important property of symmetry is anomaly. So this is very relevant to the dynamical implication. So anomaly. So anomaly would be abduction. So physically it means that it's a abduction to gauging the symmetry. Gauging the symmetry. And so how do we compute anomaly? So today I'm going to talk about how to compute anomaly. How to compute anomaly, and also what's the relevance for dynamics, and this is related to the bulk boundary correspondence. Boundary correspondence. Okay. So basically anomaly, so as I said earlier, anomaly is an abduction to gauging the symmetry. Now, what's an abduction to gauging the symmetry? So when we gauge a symmetry, we want to restrict the Hilbert space to be in the charge singlet sector. So when we gauge the symmetry, we want to impose Gauss law. Okay. So which means that we want to restrict to the like a zero charge sector in your Hilbert space. Hilbert space. Okay. So in this zero charge sector in the Hilbert space, the symmetry should act trivially. So we want to say that the symmetry acts trivially. So it should. So we want to be able to consistently restrict the Hilbert space to the zero charge sector where the symmetry actually. So this is imposing a Gauss law. Okay, but sometimes this is not possible. So sometimes not possible. Okay. So what's the situation where like this is not possible? Can I write on this? Okay. The two. Okay. So one situation is that the symmetry have a non-trivial commutation relation. So symmetry have a commutation relation. So like if you have a symmetry U, that commute with the Hamiltonian, the symmetry V, that commute with the Hamiltonian, and then they have a commutation relation given by a phase. Okay, so some phase factor here times V times U. So and then both U and V come in with the Hamiltonian. VH, maybe I should say, just write UH equal to HU, VH equal to HV. So this is U, this is V, V. Okay. And such that U and V do not commute, but they only commute up to a phase. Okay. Now, because of this phase, it's not possible to restrict the Hilbert space to the zero charge sector where both the symmetries U and V are trivially, because their commutator will give you a phase, and a phase is never trivial on the Hilbert space. Okay, so this is never trivial. So let me just say this is not equal to 1 on every state in the Hilbert space, and therefore it's not possible to restrict to the zero charge sector. Okay. Or more generally, if the symmetry defect, so you can imagine there's a, so let's say this is your space-time, and you have a defect D here. So the defect D here implements symmetry transformation inside the region enclosed by D. So here you conjugate every operators by the symmetry operator, but outside you do not do anything. So let's define for you a symmetry defect transform. Okay. So if the symmetry defect obey any non-trivial correlation function, then again you cannot restrict to the zero charge Hilbert sector in the Hilbert space because the symmetry must act non-trivial. Okay. So one situation is in one spatial dimension or 1+1 space-time dimension. So where the symmetry defect, so we can unwrap this circle into a line. Maybe I should erase something. Okay. Maybe I should go to this board. Is this board okay? Yeah. Okay. Okay. So imagine you have a symmetry defect that generates the symmetry transformation G1. So G is the elements of your symmetry group, okay, and G2 and G3, okay. And you can fuse G1, G2 into the elements G1, G2, and similarly G1, G2 can fuse with G3 into G1, G2, and G3, okay. So this is a procedure of fusing the symmetry that generates the group elements G1 and G2 and G3 into the symmetry that generates the elements G1, G2, G3. Okay. Now this is not the only way to do the fusion. So maybe I'll just erase that. So there's another way to do the fusion where you can fuse the G2 and G3 first. This is very so fuse G3, G2, G3, and then fuse with this is G2, G3, and fuse with G1, and then to G1, G2, G3. Okay. So these are different ways of fusing the G1, G2, and G3. Okay. So one way you first fuse the G1 and G2, and the second way you first fuse the G2 and G3. Okay. Now in general, this kind of fusion does not have to be exactly the same. They can differ by a phase. So again, you can differ by a phase. Okay. And again, if the phase is non-trivial, if it's not equal to the identity, then again you can conclude that you cannot consistently restrict the Hilbert space to the zero charge sector. So again, This is an abstraction. Is abstraction to gauging. Okay. Now, using it, so far I've given you 2 examples of symmetries that you cannot gauge. Namely, it's not possible to restrict to the zero charge structure in your Go.
Are you saying the
Yeah. So for the discussion today, I'm going to focus on symmetry that has an inverse. Okay. So yeah. So in particular, I'm also going to focus on symmetry that is associative. Yeah. Right. So here the symmetry is not really well. I mean, it's associative up to the associator. Okay. So the associator is well, in general it's a matrix, but for the symmetry, that is a group. The associator is a face. Okay. And this is the face I'm talking about. Yeah. Any other questions? Sorry, say that again. Right. So if you right, so when you want to project to a zero charge structure, all the symmetry acts trivially, right? So that means that all the symmetry defect should be trivial. So all the symmetry defect should be identity. Now it's obvious from this picture that if you have a face like on one side, then you cannot say all the defects are identity, right? Because there's a face on one side, there's just one on the other side, right? So you have a contradiction. Now, more precisely, there's a freedom of redefining your symmetry defect. So in general, if the face, well, I mean, the face is a co-boundary, so it will lead to some co-cycle condition, and then if the face is a co-boundary, then you can remove the face by redefining your symmetry defect. Okay. But if the face is non-trivial, then you'll get the objection to restricting the zero charge structure in the Hilbert space. Okay, so so far I've given you 2 examples of obstruction to gauging a symmetry. So now let me talk about what's the connection to double boundary correspondence. Okay. So in those examples, you can see the objections are like relations between symmetry defect. Like if I change the way to do the fusion, then there's a face. Or if I perform some commutator, then there's a face. Okay. So in general, this kind of relation can be encoded by the theory, so a theory of defects. And this theory will live in one-dimensional height. Okay. So for example, let me start with this associator and then construct a bulk theory of defects that describe those rules. Okay. So let's see, maybe let me just erase this. So I'm going to start with the symmetry, the fusion configuration on the left. Let's see. So this is like a 2D 2D space-time. This is going this way, G1, G2, G3. So so I'm going to imagine the space, this 2D space-time lives on the boundary of a 3D bulk. So imagine this is like a plane here, okay? And then it's like extending to the bulk. So all the lines will extend to a domain wall in the bulk. So, okay, not sure the drawing. So you can try to imagine your head. Like all those lines are extending to be a surface inside the 3D bulk. And on the other side, I'm going to put the symmetry defect with the other configuration. So there's another boundary here. Let's see. This is this way. This way, G1, G2, G3. And again, you extend all the lines to, well, try to imagine your head that all the lines actually need to be a surface in the bulk. And then I'm going to connect the surface that connects this G1 line to the surface that connects the G1 line here. So this is G1, this is G1, so this is G1. Okay, G1, G2, G3, G1. Okay. So so this is G2, G3. Okay, so well, you will have to imagine this a little bit. So you will. So this segment is G2, G3, okay? And this segment is the symmetry G1, G2. So maybe, okay, I have other colors. Okay, so this is G2, G3. Okay, let me use the different color. This is G1, G2. Okay. So on this boundary, there's no defects that generate G1, G2, and on this boundary, there's no defect that generate G2, G3. So that means that the surface that in the bulk that terminates on this G2, G3 must end on some point somewhere. Okay, so you will have a so you have something like, so let me just trace out the trajectory of this junction. So you'll connect to the junction here, and then you will also connect the junction over there. Okay. Now, because there's no G2, G3 symmetry defect in this configuration, and there's no G1, G2 defect in this configuration, so that means that the surface that connect to this G2, G3 must terminate somewhere at a point. And here, the surface that connect to the G1, G2 defects on the other side will also terminate on the point. Okay. So in general, if you interplay the symmetry defect on the two sides through the bulk, you'll find a single intersection point. So there's intersection point. Intersection point. Okay. And then this rule that tells you different fusion configuration of symmetry defects that differ by a phase is saying that in the bulk, if you have an intersection between the symmetry defect, like between the surfaces that connect this symmetry defect on the boundary, then you got a phase. Okay. So this defines for you a bulk theory of defects. So defines a bulk theory bulk of defects. And the definition is that when the symmetry defects intersect in a suitable way, such that the boundary are related by this kind of change, like changing the fusion configuration, then this intersection will produce a phase. Okay, so this defines for you a bulk theory. Okay. So sorry. The bulk theory is unique, yeah. So if you so you can try to connect the surface in different ways, yeah. But so in general, there can be many intersection points, but if you cancel them out, then you'll find that if you have a net intersection point, like I've counted up to size, then you'll get a phase, yeah. So of course here I have to assume many things. So I have to assume that like the defects are topological, can just move it around. So I mean sometimes if the defects are not fully topological, then the bulk might not be unique. But here I'm assuming the defects are topological. Okay.
Why do you want to change your operation with some line? Because previously you had just some break space.
So this is my definition of a symmetry defect. I'm going so let's say you are in 2D space-time, okay? So inside the region enclosed by symmetry defect, I'm going to perform a symmetry transformation. Like I conjugate every operator here by the unitary transformation, and outside do not perform anything. Okay. So this defines for you a symmetry defect, like implements a symmetry. So all of the lines here are defined this way. Yeah. So this is how the description of symmetry defects are related to the transformation in quantum mechanics that I explained earlier. Okay. So you can also construct the bulk so this is the construction of a 3D bulk from a 2D theory. You can also do the same thing for quantum mechanics. So so you can also do the same thing for quantum mechanics. So quantum mechanics only has one time direction. So in a space-time picture, just a straight line, okay? And so the symmetry defects are points. So it's an operator acting on the system at a fixed time point. So let's say, and then the computation relation tells you that so let's say this is your time direction. If you first act with V and then act with U, it's going to be different from first act with U and then act with V, and the difference would be a phase. Okay, so this is what this relation is telling you in the space-time picture. Okay. Now similarly, okay, this is B, this is B. Oh, sorry, this is U, this is V. Okay, okay. And similarly, you can construct a bulk as follows. So as as far as we did before, we just conduct the symmetry defects that during the transcend symmetry on the boundary. So if I have V here, just draw a symmetry defect in the bulk that interplay between this the symmetry defect layer here and the symmetry defect layer. Okay. And similarly, you also draw a interpolation of symmetry defect. Well, maybe let me just rather get the interplace between the other symmetries. Okay. Now you can see that no matter how you draw lines, there's going to be an odd number of intersection points. Okay. And the fact that the operators do not commute, but only commute by the phase, tells you that you can construct a bulk theory where if these two symmetry defects intersect at a point, then there's going to be a phase. Okay. So this is a bulk theory that captures these anomalies or computation relations on the boundary. Go ahead. Right, but then there's nothing. There's just one. Then there's no phase. So it's a trivial theory. It tells you that no matter the symmetry defect intersect or bright or however, there's no phase. You just like freely pass through each other. So suppose this is one. What does that tell you? It tells you that if the symmetry defect intersect, then that does not do anything. It can just freely move it away from the intersection. Right.
Like what the thing in the bulk theory that would tell you.
So the bulk theory. So in a bulk, you can ask what's the correlation function of the defects, like when they cross. Okay, so you can compute the correlation function, and when they do not commute, you'll find a correlation function equal to phase, and if they commute, you'll find a correlation function is trivial. Okay. Yeah, so you can think about bulk this way. Yeah. Yeah, so, well, I mean, in this picture, no. So if you want to kind of teach this structure, then you have to extend the symmetry in the temporal direction. Here the symmetry just acts on a fixed time moment, so it's still the original Hilbert space. So you can only have teach this structure in like at least one spatial dimension, so you can have some kind of twisted bounded condition. Okay. Like for example, like in this picture, if you insert this line like along a temporal direction, then you will get a twisted boundary condition. Then this is twisted structure. Yeah. Okay, so are there any more questions? So I'm going to go on discussing examples, or maybe we can have a 10 minutes break. I think it's almost an hour. Yeah, I don't know what's the rule like. Oh, okay. Okay, so I'm going to discuss some examples. So the first example I'm going to discuss, well, basically I'm only going to discuss quantum mechanics. This is simpler. So the first example is just a free qubit or a two-level quantum mechanics. Okay, let me just, I'm going to keep this. Okay, so it's a so the Hilbert space is like so Hilbert space is labeled by like a two-component complex vector. So this is your like one state in your Hilbert space. Okay, and the Hamiltonian 0. Okay, so it has huge amount of symmetry. It actually has SO3. But I'm going to focus on Z2 times Z2. So one of the Z2 symmetry is generated by the poly-X operator. So poly-X operator is a like 2x2 matrix in this representation acting on this two-component vector. And another Z2 symmetry is the poly-Z operator. Remember, I just write the matrix. Okay. So because Hamiltonian is 0, so they trivially are symmetries. Okay, so they commute with 0. So, and these two operators anti-commute, so x is equal to minus zx, as you can check explicitly from the matrices. So because of this sign, it tells you that these two Z2 symmetries have an anomaly, so it cannot restrict to the zero charge sector, so it has an anomaly. And this is familiar from linear algebra. So you have two matrices that do not commute, then you cannot go to the like a common eigenbasis, so they cannot be simultaneously put into the trivial charge sector. Okay. So as I said earlier, there is a relation between the anomaly in the like a bound level in quantum mechanics versus some defect theory in the book. Okay. So what's the defect theory? So in this case, you can. So I'm going to write down a bulk Hamiltonian, and tells you that if you truncate the bulk, then you're going to see this kind of symmetries that anti-commute. Okay. So the bulk Hamiltonian is the well, one bulk Hamiltonian is so-called the cluster state. So it's a so it's going to be one spatial dimension and one time dimension. So it's going to be a chain of many sites. So like 1, 2, I'm going to take the chain to be a semi-infinite. So the boundary will be this quantum mechanic system. So, and the bulk has the following Hamiltonian. So you can verify. So those Z and X are the poly operators acts on like those sites. So like Z1 is the poly Z operator acts on the Hilbert space on side 1, side 2, etc. And you can think of side 1, side 2, side 3. So each of them has a Hilbert space whose states are of this form. Okay. Okay. So first of all. So first of all, this Hamiltonian. So if you do not have any boundary, this Hamiltonian will have a unique ground state. And the reason is that all of the Hamiltonian terms are mutually commute with each other. So you can multiply. So you can minimize the each term in the Hamiltonian. So so this is mutually commuting. Okay, so you can minimize each term in the Hamiltonian. And so you have a ground state. So if you have closed chain, then the ground state will be each term equal to 1. Okay, so because I have a minus sign here, so if you want to minimize the Hamiltonian to get a ground state, each term has to be 1. Okay, and then you can use this relation to fix the spin. Sure, no problem. And we can use this relation to fix each spin to be pointing up because there's a X operator here. So there's a single ground state if the chain is closed. So there's a single constraint. Okay. But we are more interested in what happens when the chain has a boundary. Okay. So let's consider a semi-infinite chain where I start from side 1. So in this sum, I'm going to start from the index I equal to 2. So the first term would be z1, x2, x2, z3, and etc. Okay. So let's ask what are the symmetries in this model. Okay. So if you look at the this bulk Hamiltonian, maybe let me use this. So if you look at this bulk Hamiltonian, you will realize that there are two Z2 symmetry. So I'm going to call it x1 tilde and x2 tilde. And x1 tilde and x2 tilde are the product of the polyaxial operators on the outside and on the even side. Okay. And the reason it's a symmetry is that each term in the Hamiltonian has two polyZ operators. So when you try to perform the computation relation between the Hamiltonian and this part of X operator, there's going to be even number of the you are going to use even number of this computation relation. So xz become a minus zx, and because there are two, because you use the computation relation twice, so you have minus 1 squared equal to plus 1, and therefore those are symmetries of this Hamiltonian. Oh, sorry. Yeah, sorry. Let's see. Maybe okay. I can. Maybe I should just rewrite this. Okay, let me just start off x on x2, start off x even. Okay, and then maybe I should just write a term because those are going to be important. I minus 1 xi zi plus 1. Okay. So so those are the symmetries for whether it's a closed chain or open chain. Those are the symmetries because they come with the Hamiltonian, and they are later in the Z2 times Z2 symmetry because each of them are products of polyaxial pattern, and polyaxial pattern has order 2. Okay, so now let's ask what happens when there's a boundary. So let's consider a semi-infinite chain. So the Hamiltonian term, so I'm going to also write this in white. So this is z1, x2, z3. So this is the first term in this sum. So this is something, okay, this is your bulk Hamiltonian. And then similarly, there's also a term z2, x3, z4, etc. Okay. So those are the terms for the Hamiltonian on an open chain. So one end is open, and you can keep the other end finally extended. So if you look at this Hamiltonian, you'll find out this Hamiltonian on this open chain actually has a symmetry. So the symmetry is the following. So you have, okay, let me just write here. So one symmetry is x1, z2, and the other symmetry is z1. Okay. So I'm going to call this u, or maybe let me call it x tilde. So I'm going to explain the notation in a moment. Okay. So we can check that those two operators are indeed symmetry of this Hamiltonian on the semi-infinite chain. So for example, the only place where you can have a operator that involves the first side is the first term. Okay, so the terms start from z1, x2, z3, z2, x3, z4, etc. So the only thing that involves the the first side, namely involve this boundary side, is the first term. Okay. And in the first term, because there's a z1 and x2, and the symmetry operator has an x1 and z2, and because there are two, and you can use the computation relation between x and z, and check that because there are two pairs of x and z, so they commute with each other. Okay. And similarly, because the operator length of the first side is poly z, and therefore the poly z1 operator is also a symmetry that commutes the Hamiltonian. Okay. So how are those operators related to the symmetries that have been talking about? Okay. So in fact, you can check that. Well, let me first mention one thing. So this operator x1, z2 and operator z1, they obey a similar computation relation as the poly x operator and poly z operator. So this means that on this boundary, acting on this boundary side, you have this kind of quantum mechanics system where there's a z2 symmetry. Maybe let me put a tilt here. There's a z2 symmetry joined to poly x acting on this side, and another symmetry joined to poly z, and the anti-commute. Okay, so this is how we see the symmetries on the boundary. Now let me go to relate these symmetries on the boundary or to the symmetry in the bulk, namely this x1 tilde and x2 tilde that I mentioned earlier. Well, let me go to erase that. So in fact, just using a simple algebra, you can show that if you multiply x1 tilde by product of the Hamiltonian term, you can land on one of the symmetry. Okay. So recall that in the ground state, the ground state will minimize all the Hamiltonian term, and then the only Hamiltonian term here equal to +1 on the ground state. Okay. So you could multiply many terms in the ground state without changing the operator. So x1, well, let me. So let's start with x1 tilde. So recall x1 tilde is the product of the x operator at outside, and then you multiply x1 tilde by the Hamiltonian terms also at the outside. So it will be z 2j minus 1. It will be 2j minus 2 actually. 2 x2j minus 1, and then z 2j. Okay. So those are the product of Hamiltonian terms on outside. So when this middle index is on outside. Okay. So if you multiply those terms together, you'll cancel out most of the terms. So first of all, you'll cancel out all the Rx part. Okay. And what you're left with is the x when the side is on the very end of the chain. So when it's for the x1 that happens on the very end of the chain, it cannot be cancelled by the product of the Hamiltonian terms. Okay. And therefore, what you are left with is x1, z2, which is this poly x operator, this x tilde operator I've defined earlier. So this is how the symmetries on this boundary, mainly on this very edge of the chain, is related to the symmetry of the bulk. Okay. And similarly, you can take this x2 tilde, which is the product of all the poly x operator at the even side, and then multiply by all the Hamiltonian terms on the even side. So it will be 2j minus 1, x2j z 2j plus 1. So on the ground state, all those Hamiltonian terms equal to 1. But if you multiply those Hamiltonian terms with this x tilde 2 term that I defined earlier, then you'll find that basically all the x term will cancel each other because there's already a Hamiltonian term that starts from the side 2. So there's already x2 in the first Hamiltonian term. Okay. And therefore you'll end up with the poly z1 operator, and again acting on the edge of the semi-infinite chain. So this is again given by this Z tilde operator I defined earlier, which is a symmetry on a boundary. Okay. So in this way, you can see that indeed this system describes a boundary with a numbers Z2 times Z2 symmetry, which I explained in the beginning. Okay. Well, on a boundary you have, yeah, I can think, well, so you can think of the boundary as zero Hamiltonian. So this is everything coming from above, yeah.
Yeah, but boundary is one, right?
What do you mean by boundary is one?
Side one.
Yeah, boundary is side one, yeah.
Yeah, but
So this is just purely from the bulk Hamiltonian, yeah. So here I'm giving you an example of a bulk system where the boundary at side one has a Z2 times Z2 symmetry, and the Z2 times Z2 symmetry is anomalous. Okay, so this is the same anomaly as I explained earlier using this free QB example. Okay. So here the main focus is that on the boundary, namely on this edge, on this side one on the edge, you got a Z2 times Z2 symmetry generated by this X tilde and Z tilde. And this X tilde and Z tilde, they generate anomalous symmetry because they mutually anti-commute, they do not commute. Okay. Now, of course, you can have many systems with like Z2 times Z2 symmetry, and they also mutually anti-commute. And like, for example, in this free QB Hamiltonian I mentioned earlier, that's one example. And this is another example. Okay. Okay, so let's see. Okay, so now I'm going to move on to another example. So I'm going to move on to another example with fermions. So, gosh. So I want to use the pre-example to disprove several common beliefs when people talk about symmetry. So usually when people talk about anomaly. So when people talk about anomaly, sometimes they will say it can only happen in system with fermions, but I already gave you a system just like quantum mechanics that also has an anomaly. And also another common belief is that, well, maybe not so common, just some belief of some people that you can only have an anomaly in sufficiently high space-time dimension. But you can already see that in this quantum mechanics system, you already have an anomaly. And also, another more common belief is that you can only have an anomaly when the symmetry is on site. Well, when the symmetry is not on site. So on site means that your symmetry operator is a product of like operator acts on each side. So a common belief is that if the symmetry is on site, then you cannot have an anomaly. But what I just showed you earlier is just a counterexample. Namely, if you just have a single site, you just have quantum mechanics system on a single site, you can still have an anomaly. Okay, so now let me just move on to discuss fermion. So so if I have fermions, then so I'm going to call the fermion side. So the fermion has a symmetry, natural symmetry, the fermion parity symmetry. So the fermion parity acts on fermion equal to has eigenvalue -1. And if we act on all the other bosonic operator, like for example, if you have two fermion, then you got the you got +1 eigenvalue. Okay, so that's a natural symmetry in system with fermion. So I'm going to consider quantum mechanics of fermions. So let's say I'm going to consider n fermions. So let's see. So I'm going to consider psi 1 and psi n. Okay. So so they are marginal fermions. Okay. So this is quantum mechanics. And for my purpose, I'm going to let me consider when n is even and n is odd separately. So I'm going to introduce the rule. So first of all, so if n is even, then this is the system I'm going to consider. Well, when n is odd, I'm going to add additional marginal fermion. So that's just to make sure that the total number of fermion is even, and this extra marginal fermion is not going to do anything. Okay. So from this marginal fermion, I can define the creation and annihilation operator. So I can define, maybe there's a square root 2 here. Minus 1 plus I. Okay. And then C I dagger is just defining a similar way with the conjugate. Minus I. Maybe I shouldn't use the I here. Let's just say this is J. This is J. J here. And they obey the usual commutation relation. So Cj, Ci, maybe I should use I here. Dagger, like the anti-commutator, equals to Lij. So this is going to be my normalization. And here the those C's will have index runs from like 1, 2, 3, etc. up to over 2. So okay, so here I'm going to maybe let me first assume n is even. So this is easier. Okay. So from this fermion, I can define a compact fermion. And then this is the creation and annihilation operator of my states in the Hilbert space. Okay. Now, in addition to fermion parity, there's also another symmetry in the quantum mechanics system of fermion, namely the tensor symmetry. So the tensor symmetry, well, and we are going to study what's the relation between tensor symmetry and this fermion parity symmetry. Okay. Okay, so so first of all, I'm going to let's see. Okay, so first of all, I'm going to say this is my tensor symmetry. So tensor symmetry acts on Ci by conjugation equals to the Ci dagger. Okay. So this is the tensor symmetry of the quantum mechanics system of the marginal fermions. Okay. So basically, you replace the creation operator with the with the annihilation operator. Okay. So first of all, this is the tensor symmetry. Now from this definition, I'm going to compute what's the relation between this tensor symmetry and the mass 1 to the F symmetry. Okay. So let me just I have to erase some of it. Maybe let me erase this. Okay, so in order to compute the relation, in order to derive the relation between this tensor symmetry and the fermion parity symmetry, I'm going to study how the symmetry acts on the state in the Hilbert space. Okay. So what are the state in the Hilbert space? Well, you have a free Fermionic system, so you can build the flux space from the creation annihilation operator. So you start with 0, the flux space vacuum that is annihilated by all the all the CI over there. And then you start building like more like other states, like 1 fermion, 2 fermion states by acting with the creation operator. Okay. Now let's consider how the tensor symmetry acts on this state. So there's a tensor symmetry acts on this state. So obviously it has to be 0. Well, because the state itself is 0. Okay. So this is 0. Now on the other hand, if you use this relation for tensor symmetry, so then let me just copy it again. So now let me use the relation that T Ci T inverse equal to Ci dagger. So now let's use this relation between tensor symmetry and fermion to rewrite this relation as follows. So you can replace Tc by Ci dagger, Ci dagger T. Okay. So here I'm just replacing this Tc with the Ci dagger T. Okay, using the definition of tensor symmetry. So what does that mean? Well, it tells you that the state that is acted by the tensor symmetry will be annihilated by all the creation operator. Okay. So this tells you that the state acting on the tensor symmetry will equal to some phase, so some phase, and then you just put all the then you just act on the flux space vacuum with all the creation operator. So 2. Okay. So this is the top state in your flux space. Here, if your flux space, and this is the state that is annihilated by all the creation operator. Okay. Okay. So now we can do several things. Well, in principle, it could be well, if you start with just a free fermion flux space, then this is non-zero. Yeah. Okay, so this is the state that's created, that's produced by tensor symmetry. Now you can see the following property. So you start from the 0 state without any fermion, and the state now has over 2 number of fermions. So and therefore this state will be fermionic if n over 2 is an odd number, and the state will be bosonic if n over 2 is an even number. Okay. So that tells you -1 to the f will equals to over 2 t. Okay. So so the state 0 has 0 fermion, but now when you act with tensor symmetry, suddenly you have over 2 fermion. So that means that there's a computation relation between the -1 to f and tensor symmetry. So this is -1 over 2 -1. Did I? Okay, this is the ordering. Okay. So that tells you that if n is like 2, 6, etc., then the tensor symmetry and -1 to f will anti-commute with each other. So 2, 6, 10, da 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 da. So that's one example of anomaly in fermion quantum mechanics. Okay. So maybe let me go through the argument again, because it might be a little bit fast. Okay. So I begin with a system with n marginal fermions. So the system has a -1 to f symmetry. The definition is that the -1 to f acts on states with a number of fermions. It'll give you -1. An even number of marginal fermion, it'll give you +1. In addition, the system has tensor symmetry. So if you pair the major fermions, so now let me assume as even for a moment. So if you pair up the major fermions into the creation annihilation operator acting the Fock space blocking, then the tensor symmetry will conjugate we will change the annihilation operator to creation operator and vice versa. Okay. And can build the Hilbert space starting from the zero state, which is annihilated by all the annihilation operators Ci. So recall that Ci is related to the major fermion in this way. So it's combination of like pair of major fermion with the factor I. And starting from the zero state, you can build up all the other states in the all other states in Hilbert space by acting with the creation operator. So where is it? Where's my chalk? So you can start with the zero state and then build the like one fermion state by acting with the creation operator on the zero. So this is going to be a state with one fermion. And similarly, you can also like Cy dagger, C2 dagger, 0, and then have two fermion states, etc. Okay. Okay. And we want to compute the computation relation between the tensor symmetry and fermion parity symmetry. So what I'm going to show is that the tensor symmetry will change the fermion parity of the state. So if the state in the beginning is a bosonic state, then acting with the tensor symmetry can change it to be a fermionic state with R number of fermions. Okay, so this is like if you have R number of fermion, then this is like a fermionic state. And if you have even number of fermions, then this is like bosonic state. Okay, so argument is the following. So let's say you start with the zero state, namely the state that is annihilated by all the annihilation operator, and then you can apply the tensor symmetry. So if the state, so this is 0, so apply T again, you still got 0. But now we can use the computation relation to relate the TC where the C is the fermion annihilation operator with C dagger T. So this is just using the definition of tensor symmetry. And then this tells you that if you start with the zero state and apply the tensor symmetry, you are going to end up with the top state in your Fock space, namely the resulting state will be annihilated by all the creation operator. Okay. So that tells you that T action 0 will give you the top state. Now because you can define a state after a phase, so here I put a phase factor here. And the top state is starting from the zero state in your Fock space, and then apply all the creation operators. So recall that there are n major fermions. So here I'm going to assume n is even. So there are n over 2 creation operators given by pairing the major fermions. So we have C1 dagger, C2 dagger, etc. up to C over 2 dagger. And this top state has n over 2 fermions. And therefore, depending on whether n over 2 is even or odd, the state is a fermionic state or bosonic state. Okay. So when n is 2 more 4, so like if n is 2, 6, 10, I can also keep going on. Let's see, so 14, etc. If n is 2 more 4, then over 2, and then n over 2 is odd. So that tells you that you start from a state with 0 fermion, then suddenly you got a state with an odd number of fermion. Okay. So that tells you that when n over 2 is odd, the tensor symmetry and fermion parity symmetry will anti-commute with each other. Okay. And when n over 2 is even, and then if n is 0 more 4, then the state is still a bosonic state. So that tells you that the tensor symmetry and fermion parity symmetry still commute with each other. Okay. So from this computation, you can show that. So basically, you already found that if n is 2 more 4, then this quantum mechanics of fermions has an anomalous symmetry, anomalous tensor symmetry and fermion parity symmetry, because tensor symmetry and fermion parity symmetry intercommute. So this is similar to the quantum mechanics example I discussed earlier. So now we can ask, like, what happened to the other end? So let's see. Okay. So I'm going to make a table. So here, so let me start with n equal to 1, 2, 3, 4, 5, 6, 7, etc. So, okay. I'm going to circle the case with anomaly. So we see that when n equal to 2 more 4, 2, 6, etc. It has anomaly. Okay. So how about all the values of n? So here I'm going to focus on n is even. So I'm going to forget about the Rn for a moment. Okay. So let's compute t squared. Oh, okay. Yeah, I'll just erase it. Well, let's see. I can erase this. Okay, so here I told you what's the action of t on the state in your Hilbert space. Okay. So now I'm going to perform t twice. I'm going to compute t squared. So if you look at the definition of the action of t, you can realize that, so basically t exchanges the correlation operator with annihilation operator. So at the level of operator, if you do it twice, things that you just go back to the original thing. Okay. But now if you compute t squared, so well, first let me remark that on the operator level, so we have t squared equal to 1. Okay, so because t just exchanged the correlation with operator with annihilation operator. But what happens when the tensor symmetry act on a state? So from this action of t on the 0 state, I can compute t squared on the 0 state. So then you just do just compute the action twice. Okay. So I probably need a longer. So here I'm just copy the action. So e to I alpha. C2 dagger, C1 2 dagger 0. Okay, and so just go step by step. So this is equal sign here. So and then you just apply the t on each turn. So if you move the t through the face, you just plus conjugate it minus I alpha. And if you move t through the other thing, we just change it to be the correlation operator. So C1, C2, C over 2. Okay, so just move the t until it hits on the 0 state again. And then you can apply the rule. So the t acts on the 0 state will give you the top state up to this phase. Okay, so maybe erase this. So here I'm just going to use the formula again for this t acting on 0. So first let me copy the previous structure. So e to I alpha minus I alpha C1 C2 over 2, and then you have e to I alpha have C1 dagger C2 dagger C over 2 dagger. Okay, I don't 0. Okay. So let's try to simplify the expression. So first of all, you can just kill the overall phase factor. It doesn't matter. And later on, we are going to use the property that all the annihilation operator will kill the zero state. But if you want to, so in order to kill the zero state, we want to move the annihilation operator to be active on the zero state, and we want to swap the position of all the annihilation operator with the correction operator. Okay. So for example, I can move the CI dagger pass through this n over 2 number of annihilation operator to the very left, and then I can move the C2 dagger operator also to the left of the left of C2. Okay. So in the end, so and each time when you exchange the each time when you exchange the C1 like CI dagger with Cj, where j is not equal to j does not equal to I, you're gonna modify because the computation relation. Maybe let me just write down again. So Ci Cj dagger and the computation relation equal to delta Ij. So you just use this computation relation repeatedly, and then you'll find out you got a sign. So maybe let me erase this. Okay. So you got a sign which is minus 1. So we have over 2 plus over 2. Well, this is a bit tedious. Over 2 minus 1 plus 0. Okay. So the first over 2 is because we have to move the the CI dagger path through least many of fermions. So here actually I have a minus 1 here. Minus 2. Okay. So I want to move the CI dagger path through like C2, C3, etc. to C over 2. Okay. And then similarly for C2 dagger, you have to move it path through C3, C4 up to C over 2. Okay. So that's why you have over 2 minus 1 and over 2 minus 2, etc. and until you reach 0. Okay. So and then you can just sum up the exponent factor. So maybe let me denote k equal to over 2. So let me just use a shorthand notation. So then you have minus 1 sum k minus 1 plus k minus 2, and the summing up to 0. Okay. I'm going to continue over there. So you'll find that t squared equal to 0 equal to minus 1 k minus 1 k over 2 k on 0, okay, for k equal to over 2. Okay. Now you can simplify expressions a bit. So well, let me. Okay, I'm not sure this is. Maybe let me erase that part. So this is more visible. And then let me copy the equation again. Minus 1, okay, so this is k minus 1 over 2. Maybe let me also copy the t squared over there. So we have t squared acting on 0 equals to minus 1 k minus 1 times k over 2 and 0 here. And then because k equal to over 2, so let me just substitute this. Minus 1 to the over 2 minus 1 over 2, and then there's a half. Okay. 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 So basically, this will give you plus 1 or minus 1 because this. So this is the product of two consecutive number. So n over 2 times n over 2 minus 1, and then divided by 2. So you will get the minus 1 is equal to 4 more 8. where's the eraser? So you got a -1 for n equal to 4 more A over 6 more A. Okay. So you can plug in this relation. So for example, if n equal to 2, if n equal to 2, then over 2 -1 is 1, then over 2 is 2, and 2 cancel out with the 1/2 here. So we got -1 to the 1, which is -1. And similarly, if n equal to 6, so 6 n over 2 -1 equal to 2, which cancel with the half here, and over 2 gives you 3. Again, it's an odd number, so we got a -1. Okay. So previously, you have seen that there's an anomaly for n equal to 2, 6, etc. But now we see that n equal to 4 also has an anomaly. So there's a new thing. Now we know n equal to 4 also has an anomaly.
So in this case, we get -1. It feels like maybe there is t squared equals 1 and has this 0 state.
So here, what happened is that even though on the operator level t squared equal to +1, but when you act on a state, actually you find t squared equal to -1 acts on the certain state. Okay. So this is similar to the anomaly I've been talking about. So anomaly is that when you have symmetries like Z2 times Z2 symmetries that do not act as a Z2 times Z2 symmetry when you will look at their action on the Hilbert space. Okay. So even though we have a tensor symmetry which is naively Z2, but you find out when its action on the Hilbert space is actually Z4 when n equal to 4 more A or 6 more A.
Is this different when you say the G operators don't communicate because they not
Yeah.
This is a separate.
This is the same phenomena. This is the same phenomena. So well, let me state this abstractly so you can relate the two things. So let me state this abstractly. So let's say you have a quantum mechanics system with a symmetry like that can be labeled by some group, okay? And there is an operator that corresponds to the symmetry that generates the symmetry for each element in the group, okay? Now suppose you find that the operator acts on a Hilbert space. So let's say there's some state here, okay? It does not obey the group multiplication law. So so group multiplication law tells you that if you multiply the operator that generates the symmetry for elements G1, an operator that generates the symmetry for G2, you should get the operator that generates the symmetry for their product G1, G2. Okay, but because in quantum mechanics you can only define a state up to a phase, so in general there can be a phase here. Okay. Right. So in the case when the two symmetry, so for example if you start with a symmetry like Z2 times Z2, so if the symmetry is Z2 times Z2, then every element in like Z2 here and Z2 there should commute with each other, right? But the fact that they intercommute when they act on the Hilbert space is that there's a non-trivial phase here. Okay. Now similarly, if the symmetry start with the Z is Z2, like the terms of symmetry over there, but you realize that when the symmetry acts on the Hilbert space, it actually becomes a Z4 symmetry. Like there's a non-trivial minus sign here or non-trivial phase here. Then this is again described by this non-trivial. So as long as the phase is non-trivial, then you got an anomaly for the symmetry. Yeah. So this is true for like both this case and the case I've been talking about like earlier. Yeah. Okay. I'm not sure. Let's see. It's a bit annoying. I'm not going to do that. I mean, it's a bit annoying. Yeah, so for my case, I'm going to always keep the number of fermions even. So even if you have odd number of fermions, I'm going to either decouple extra fermion. So you can have a well-defined Hilbert space. So here, the Hilbert space is crucially related to the fact that you have creation and annihilation operator. So you can build up the Fock space vacuum and then just build like one fermion state, two fermion state, etc. So I'm always going to keep the number of major fermion even. Okay. So if you start with a odd number of major fermion, I'm going to add extra decoupled fermion, and then you can run the same story. Okay. So well, let me just comment a little bit about the book boundary correspondence. So I'm not going to discuss this in detail. Let's see. So well, let me first just summarize what we have so far. So we start with some even number of marginal fermions, and then we realize that as long as the number of fermions is not a multiple of 8, then there's always some violation of the symmetry relation. So there's always some phase here when you study how the symmetry acts on the Hilbert space. Okay. So a short summary here is that if n is not a multiple of 8, then you have an anomaly for transversal and -1 to the f. Okay. 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 So now let me just go on to talk about the bulk boundary correspondence. So sure.
When you say anomaly, there is a problem when they want to gauge it.
Yeah.
So then gauging what is infected, each side is different than the ortho.
Right. So maybe let me comment about what happened for this case. So when I talk about gauging T, is that you can consistently introduce the transversal defect. So imagine you have some space, and there's a domain wall. Like when you pass through the domain wall, you reverse the direction of time. So evolve the time like in the opposite way, like on two sides of the domain wall.
Some wet side and the kind
That's right. That's yeah. With the opposite, right. And then the statement that you can gauge the time symmetry means that you should be able to introduce like any configuration of domain wall in a consistent way. Okay. Now the problem here is that like for example, if the t and -1 to f does not commute, it tells you that like it tells you that in this case if you have like sort of two different fermion priority on the two sides, so let's give you some inconsistency. And also if t squared is not equal to 1 on the Hilbert space, it tells you that, well, if you start with a like Z2 domain wall, if you fuse two domain wall, you don't exactly got the got +1, but there's some residual minus sign. Yeah. So that tells you there's some inconsistency of introducing this kind of transversal domain wall in the system. Right. Okay, so let me just briefly comment about the bulk boundary correspondence. So I'm just going to tell you the bulk theory without explaining this in too much detail. So bulk boundary correspondence. Okay. So previously, well, I have constructed the example. This cluster state example. They found like 1D chain with some polymatrices generate symmetries on the edge. Okay. Now you can do similar things here, and instead of the cluster state Hamiltonian, you have the Kitov chain. So it's called Kitov chain. Okay. And so basically, it's a again, it's a sum of like some Fermionic operator. Okay. So here I'm going to be very schematic. Okay. So basically, the Hamiltonian is a so first of all, it's a free Hamiltonian. Namely, Hamiltonian is quadratic in the Fermionic operator. So maybe I should use psi here. This is psi. Psi 9 plus 1, da, 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 da. Okay, so there are many terms. And maybe there's a coupling here. Okay. So this is a free Fermionic system living on a chain. And when the chain is closed, like there's no boundary, again there's a unique ground state. But when the chain has a boundary, so let's say again there's some h side here, then there's some h marginal fermion here because you just truncate the chain. Okay. And this h marginal fermion will have this kind of anomalous symmetries. Okay. So this is called Kitov chain. So here I'm being very schematic. Okay. We also let's see, we have half an hour. So maybe let me talk about the response theory. Okay. So maybe let me talk about. Okay. So let me talk about this bulk boundary correspondence in a more precise way. So recall that in the Z2 times Z2 case, so in the previous example, okay, let me first, well, maybe let me not use this blackboard. So maybe let me erase this. Oh, shit. So let me talk about the bulk boundary correspondence in more detail. Response. I mean, I can end here if everyone is happy. I can talk about the rest next time. So it's your choice. So should I end here and we can have pizza or continue forward? Well, maybe just give me 5 minutes. Okay, I will wrap up in 5 minutes. So let me talk about response theory. So the response theory is a way to describe what's the it's a way to describe what's the like what's the coefficient function of defect. So coefficient function. Okay. So let me use the free QB Hamiltonian as an example. So this is just a free two-state system. So the system can be described by an action. So quantum mechanics is a special case of quantum field theory, so we can describe it by action. And the degree of freedom are some scalars, so it should be a Z2 value scalar. And you can describe the Z2 value scalar by this kind of period. So you can describe the Z2 value scalar by two scalars. that are conjugate to each other. Okay. So together, let's describe the Z2 values together. So Z2. Okay. So the theory has Z2 times Z2 symmetry. So those are the shift symmetry of the scalar. So 1 go to phi 1 plus alpha 1. Phi 2 go to phi 2 plus alpha 2. So when alpha 1 and alpha 2 are constant, then that will leave the actual invariant. So those are the Z2 times Z2 symmetry. So now let's ask if we can gauge the symmetry. So if you gauge the symmetry, we want to introduce a gauge field. So if you introduce the gauge field, so the gauge field we also transform like A1 equals A1 minus D of alpha 1, A2 goes to D alpha 2, okay? So now we can ask whether you can consistently introduce the gauge field, okay? So where now alpha 1 and alpha 2 can depend on the position, well, depends on the time because there's just one coordinate. And, right, so so the reason is that I put a particular coefficient here, like 2 over 2 pi, okay? And this tells you that if you integrate all phi 2, for example, then phi 1 can only be value 0, 2. So, well, I mean, so if you so let me tell you what happened. So if you shift phi 1 by arbitrary, so let's say if you shift phi 1 by arbitrary alpha, well, I mean, you can exchange the D recurrence. Let me just discuss one case. So if you shift phi 1 by arbitrary alpha 1, so now the action will change by integral of the alpha 1 of the phi 2. Right, so if you shift phi 1 by alpha 1, we change by this. Now, because phi 2 is like some, so phi 1 and phi 2 here are periodic angular variable, okay? So that tells you that d phi 2 will give you some like 2 pi times integer, right? Because of this angular variable. So that tells you that only when alpha 1 is 0 pi, this action is invariant. Otherwise, it's not invariant. Right? So if you consider a profile of phi 2, that gives you a winding number like 2 pi times n, then this action will give you like 2. So let's say alpha 1 is some constant. Will give you 2 alpha 1 times n, right? So so suppose alpha 1 is like some arbitrary fraction, then this is non-invariant. That is not a 2 pi integer, right? Only when alpha 1 equal to 0 pi, then this will be a 2 pi integer. So you want this thing to be 0 mod 2 pi. Then what's the condition on alpha 1? Right. So so recall that the action appear in your path integral as e to the is, right? So this is a particle of d phi 1, d phi 2, and then e to the is. So therefore, if oh yeah, of course, it's just fine. Yeah, sure. Sorry? But n here is arbitrary. So n here depends on what's the profile. So n here is the winding number of profile phi 2, which I can choose arbitrary because in the path integral you can choose arbitrary phi 2. So in the path integral, they are going to be decomposed into infinite many sectors depending on what's the winding number of n here. So there's going to be some of a sector where n equal to 0, sector n equal to 1, sector n equal to 2, sector n equal to 3, etc. Right? So because we want to have a symmetry for every sector, and therefore you should get a statement that does not depend on n there, because n here is arbitrary. N here depends on the profile of phi 2. N is arbitrary integer. So if phi 1 is 2, then you have 4n, right? But 4n is not 0 mod 2 pi, right? So the only consistent answer is alpha equal to 0 or pi, modulo 2 pi, right? So first of all, alpha, so because phi is 2 pi periodic, so alpha is also 2 pi periodic. right? And alpha 2 is also, of course, also 2 pi periodic. Yeah. Yeah.
I see. So
Right. So basically, well, so maybe let me also emphasize again. So phi here is 2 pi periodic, and alpha 1, alpha 2 are also 2 pi periodic because of that. Okay. Great. So if you introduce a gauge field, so A1, A2, and now we can alpha 1 and alpha 2 to be arbitrary function of time. Of course, they also have to be 2 pi periodic. And then if you transform phi in this way, then this gauge field A1, A2, we also have to transform this way. Okay. But now you will encounter a problem, namely, there's no way to just couple a system to the gauge field A1, A2 while maintain the symmetry. Okay. Now to understand the problem, you can rewrite the system as a 2D system. So so let's imagine there's a bulk. Then you can replace the system by the following. Okay. So here is the wedge product, if you like. Okay. So this is you can think of as a bulk boundary system. Okay. Now this action written this way is manifestly invariant under the transformation. Right. So well, maybe I should put a plus sign here. Okay. And then if you expand this action, so you'll get some boundary term. So it can be, I don't know, phi 1 d phi 2 plus A2. And maybe you can also have a phi 1, maybe A1, phi 2, etc. Now the point is that there's going to be a bulk term, A1, A2, and there's a coefficient over 2 pi. Okay. Now the point is that while with a bulk, you can gauge the symmetry consistently, and then introduce a gauge field, and then maintain the gauge invariance. But this cannot be written just as a pure boundary term. So if you try to integrate, so imagine this is a bulk with boundary, you can try to write it as a boundary term, but there's always a non-trivial bulk term. Okay, so the bulk term tells you. So the bulk term is given by just A1 wedge A2, if you like, where A1, A2 are the gauge field. And this bulk term is non-trivial for general gauge field configuration. So here you can show that. So first of all, let me make two statements. So first of all, here A1, A2 can just be a classical probe field. So I have so this A1, A2 does not have to be dynamical. So it's just some classical probe field. So this A1, A2 represent the symmetry defects that I've been talking about. And here you can show. So here you see that the theory cannot couple to the gauge field consistently, just purely in the quantum mechanics system. It can only couple the gauge field consistently if you have a bulk. And the reason is that there's a non-trivial bulk term. And this is the bulk term that corresponds to the anomaly of the Z2 times Z2 symmetry in quantum mechanics. So what's the nature of the bulk term? So the bulk term, well, as I wrote it here, is integral of A1, A2. So if the gauge field is A1, A2, then the action is integral of A1, A2. Now, when is this action non-trivial? This action is non-trivial when the, well, let me erase this. So when is this action non-trivial? Well, A1, A2. Okay. So now I'm going to use the following trick. So what's the meaning of the gauge field? Well, the gauge field is that if you have a symmetry defect, and then so let's imagine your space-time is a lattice. Okay, so there are many links. Now for the links that are cut by the symmetry defect, you have a non-trivial gauge field. So if you have a defect that generates the first Z2 symmetry, then there is going to be non-trivial gauge field living on those links. Okay, And for other links, the gauge fields are trivial. And certainly, for any links that is cut by the symmetry deflux for the second Z2, you have a non-trivial gauge field A2. Okay. So this tells you that this integral of A1, A2 is actually computing the intersection number of the so the e to the this action is actually computing -1 to the intersection number of the symmetry defect. Okay. So this is something you can just compute explicitly because of this relation. So this relation is called Poincare duality. So you can use Poincare duality to compute intersection from this response action. So this is more quantitative way to characterize the thing I mentioned earlier about the bulk boundary correspondence. Okay, so. So here the mixed term, so here you have some mixed term, but you can write a mixed term into a boundary term using the properties of the gauge field. So here gauge field, so here I throw under the rug a little bit. So here the gauge field will also be Z2 value. So then if you integrate the gauge field, then it will also be 0 pi mod 2 pi. Okay. So if you use this property, then you can rewrite the mixed term into a boundary term this way. So the intuitive reason is that because the symmetry is Z2, so the gauge field will not have any will not have any non-trivial field strength because the symmetry is Z2. Okay, so locally the field strength will be 0. And then using this property, you can rewrite the mixed term to the some boundary term. But the point here is just that you must have a non-trivial bulk term because the term A1 times A2 is non-trivial and is given by the intersection number. So in the bulk, you extend everything to the bulk. And if you can write everything on the boundary, then you write everything on the boundary. Okay, I guess we'll stop here. Can I have pizza?